Learning objectives. In this chapter, the user would learn the following aspects of interrupt service routines: watchdog timer, flash memory basic toolset, hosts and debugging, remote debugging, ROM emulator, logic analyzer, caches, computer optimization, statistical profiling. Watchdog timer. A watchdog timer is an electronic timer that is used to detect and recover from computer malfunctions. During normal operation, the computer regularly restarts the watchdog timer to prevent it from elapsing or timing out. If, due to a hardware fault or program error, the computer fails to restart the watchdog, the timer will elapse and generate a timeout signal. The timeout signal is used to initiate corrective action or actions. The corrective actions typically include placing the computer system in a safe state and restoring normal system operation. Most embedded systems need to be self-reliant. It is not usually possible to wait for someone to reboot them if the software hangs. Some embedded designs, such as space probes, are simply not accessible to human operators. If their software ever hangs, such systems are permanently disabled. In other cases, the speed with which a human operator might reset the system would be too slow to meet the uptime requirements of the product. A watchdog timer is a piece of hardware that can be used to automatically detect software anomalies and reset the processor if any occur. Generally speaking, a watchdog timer is based on a counter that counts down from some initial value to 0. The embedded software selects the counter's initial value and periodically restarts it. If the counter ever reaches 0 before the software restarts it, the software is presumed to be malfunctioning and the processor's reset signal is asserted. The processor and the embedded software it's running will be restarted as if a human operator had cycled the path. Architecture and operation. Watchdog restart. The act of restarting a watchdog timer is commonly referred to as kicking the dog or other similar terms. This is typically done by writing to a watchdog control port. Alternatively, in microcontrollers that have an integrated watchdog timer, the watchdog is sometimes kicked by executing a special machine language instruction. An example of is the CLRWDT instruction found in the instruction set of some PIC microcontrollers. In computers that are running operating systems, watchdog resets are usually invoked through a device driver. For example, in the Linux operating system, a user space program will kick the watchdog by interacting with the watchdog device driver, typically by writing a 0 character to /dev/watchdog. The device driver, which serves to abstract the watchdog hardware from user space programs, is also used to configure the timeout period and start and stop the timer. Single stage watchdog. Watchdog timers come in many configurations and many allow their configurations to be altered. Microcontrollers often include an integrated on-chip watchdog. In other computers, the watchdog may reside in a nearby chip that connects directly to the CPU, or it may be located on an external expansion card in the computer's chassis. The watchdog and CPU may share a common clock signal as shown in the block diagram below, or they may have independent clock signals. Multi-stage watchdog. 2 or more timers are sometimes cascaded to form a multi-stage watchdog timer, where each timer is referred to as timer stage or simply a stage. For example, the block diagram below shows a 3-stage watchdog. In a multi-stage watchdog, only the first stage is kicked by the processor. Upon first stage timeout, a corrective action is initiated and the next stage in the cascade is started. As each subsequent stage times out, it triggers a corrective action and starts the next stage. Upon final stage timeout, a corrective action is initiated, but no other stage is started because the end of the cascade has been reached. Typically, single-stage watchdog timers are used to simply restart the computer, whereas multi-stage watchdog timers will sequentially trigger a series of corrective actions with the final stage triggering a computer restart. Kicking the dog. The process of restarting the watchdog timer's counter is sometimes called kicking the dog. The appropriate visual metaphor is that of a man being attacked by a vicious dog. If he keeps kicking the dog, it can't ever bite him, but he must keep kicking the dog at regular intervals to avoid a bite. Similarly, the software must restart the watchdog timer at a regular rate or risk being restarted. Corrective actions. A watchdog timer may initiate any of several types of corrective action, including processor reset, non-maskable interrupt, maskable interrupt, power cycling, fail-safe state activation, or combinations of these. Depending on its architecture, the type of corrective action or actions that a watchdog can trigger may be fixed or programmable. Some computers, for example PC compatibles, require a pulsed signal to invoke a processor reset. In such cases, the watchdog typically triggers a processor reset by activating an internal or external pulse generator, which in turn creates the required reset pulses. In embedded systems and control systems, watchdog timers are often used to activate fail-safe circuitry. When activated, the fail-safe circuitry forces all control outputs to safe states to prevent injuries and equipment damage while the fault persists. In a two-stage watchdog, the first timer is often used to activate fail-safe outputs and start the second timer stage. The second stage will reset the computer if the fault cannot be corrected before the timer elapses. Fault detection. A computer system is typically designed so that its watchdog timer will be kicked only if the computer deems the system functional. The computer determines whether the system is functional by conducting one or more fault detection tests, and it will kick the watchdog only if all tests have passed. In computers that are running an operating system and multiple processes, a single simple test may be insufficient to guarantee normal operation, as it could fail to detect a subtle fault condition and therefore allow the watchdog to be kicked even though a fault condition exists. Upon discovery of a failed test, the Linux watchdog daemon may attempt to perform a software-initiated restart, which can be preferable to a hardware reset, as the file systems will be safely unmounted and fault information will be logged. However, it is essential to have the insurance of the hardware timer, as a software restart can fail under a number of fault conditions. In effect, this is a dual-stage watchdog with the software restart comprising the first stage and the hardware reset the second stage. Dog days. A watchdog timer is a useful tool in helping your system recover from transient failures. Since it is so common to find watchdogs built into modern microcontrollers, the technique is effectively free. If you are working on a mission-critical system, then either common sense or regulatory body will insist that you use a watchdog. It's always a good idea to make your systems more self-reliant. Flash memory. Flash memory is an electronic non-volatile computer storage medium that can be electrically erased and reprogrammed. There are two main types of flash memory, which are named after the NAND and NOR logic gates. The internal characteristics of the individual flash memory cells exhibit characteristics similar to those of the corresponding gates. EPROMs had to be completely erased before being rewritten. NAND type flash memory may be written and read in blocks which are generally much smaller than the entire device. NOR type flash allows a single machine word to be written to an erased location or read independently. Principles of operation. Flash memory stores information in an array of memory cells made from floating gate transistors. In traditional single level cell SLC devices, each cell stores only one bit of information. Some newer flash memory known as multi-level cell MLC devices, including triple level cell TLC devices, can store more than one bit per cell by choosing between multiple levels of electrical charge to apply to the floating gates of its cells. The floating gate may be conductive or non-conductive. Floating gate transistor. In flash memory, each memory cell resembles a standard MOSFET, except the transistor has two gates instead of one. On top is the control gate, CG, as in other MOS transistors, but below this there is a floating gate, FG, insulated all around by an oxide layer. The FG is interposed between the CG and MOSFET channel. Because the FG is electrically isolated by its insulating layer, any electrons placed on it are trapped there and under normal conditions will not discharge for many years. When the FG holds a charge, its screens partially cancels the electrical field from the CG, which modifies the threshold voltage VT of the cell. More voltage has to be applied to the CG to make the channel conduct. For readout, a voltage intermediate between the possible threshold voltages is applied to the CG, and the MOSFET channel's conductivity tested if it's conducting or insulating, which is influenced by the FG. The current flow through the MOSFET channel is sensed and forms a binary code reproducing the stored data. In a multi-level cell device which stores more than one bit per cell, the amount of current flow is sensed rather than simply its presence or absence in order to determine more precisely the level of charge on the FG. Internal charge pumps. Despite the need for high programming and erasing voltages. Virtually all flash chips today require only a single supply voltage and produce the high voltages via on-chip charge pumps. Over half the energy used by a 1.8 volt NAND flash chip is lost in the charge pump itself. Since boost converters are inherently more efficient than charge pumps, researchers developing low power SSDs have proposed returning to the dual VCC or VPP supply voltages used on all the early flash chips, driving the high VPP voltage for all flash chips in an SSD with a single shared external boost converter. In spacecraft and other high radiation environments, the on-chip charge pump is the first part of the flash chip to fail. Flash memories continue to work at much higher radiation levels in read-only mode. NOR flash. In NOR gate flash, each cell has one end connected directly to ground and the other end connected directly to a bit line. This arrangement is called NOR flash because it acts like a NOR gate. When one of the word lines is brought high, the corresponding storage transistor acts to pull the output bit line low. NOR flash continues to be the technology of choice for embedded applications requiring a discrete non-volatile memory device. The low read latencies characteristic of NOR devices allow for both direct code execution and data storage in a single memory product. Programming. A single level NOR flash cell in its default state is logically equivalent to a binary 1 value because current will flow through the channel under application of an appropriate voltage to the control gate so that the bit line voltage is pulled down. A NOR flash cell can be programmed or set to a binary 0 value by the following procedure. An elevated on voltage, typically more than 5 volts, is applied to the CG. The channel is now turned on, so electrons can flow from the source to the drain, assuming an NMOS transistor. The source drain current is sufficiently high to cause some high energy electrons to jump through the insulating layer onto the FG via a process called hot electron injection. Erasing. To erase a NOR flash cell, a large voltage of the opposite polarity is applied between the CG and source terminal, pulling the electrons off the FG through quantum tunneling. Modern NOR flash memory chips are divided into erase segments. The erase operation can be performed only on a blockwise basis. All the cells in an erase segment must be erased together. Programming of NOR cells, however, generally can be performed one byte or one word at a time. NAND flash. NAND flash also uses floating gate transistors, but they are connected in a way that resembles a NAND gate. Several transistors are connected in series and the bit line is pulled low only if all word lines are pulled high above the transistor's PT. These groups are then connected via some additional transistors to a NOR style bit line array in the same way that single transistors are linked in NOR flash. Compared to NOR flash, replacing single transistors with serial link groups adds an extra level of addressing. Whereas NOR flash might address memory by page, then word, NAND flash might address it by page, word, and bit. Bit level addressing suits bit serial applications such as hard disk emulation, which access only one bit at a time. Execute in place applications, on the other hand, require every bit in a word to be accessed simultaneously. This requires word level addressing. In any case, both bit and word addressing modes are possible with either NOR or NAND flash. Limitations: block erasure, memory wear, read disturb, X-ray effects. Debugging techniques. Some reasons why you can't test on the target machine. Test early. Target may not be ready or completely stable. Exercise all code, including exceptions. Real situations may be difficult to exercise. Develop reusable, repeatable test. Difficult to do in target environment and likelihood of hitting the same bug is low. Store test results. Target may not even have disk drive to store results. Basic techniques. Target system on the left. Hardware in-depth code. Hardware depth code. Hardware test system on host on the right. Hardware in-depth code. Same scaffold rest. Scaffold provides in software all functionalities and calls to hardware as in the hardware depth and hardware components of the target system, more like a simulator for them. Embedded systems are interrupt driven, so test based on interrupts. Divide interrupt routines into two components, a component that deals with the hardware, a component of the routine which deals with the rest of the system. To test, structure the routine such that the hardware dependent component A calls the hardware independent part B. Write component B in C language so that the test scaffold can call it. Calling the timer interrupt routine. Design the test scaffold routine to directly call the timer interrupt routine rather than other part of the host environment to avoid interruptions in the scaffold's timing of events. This way, the scaffold has control over sequences of events in the test which must occur within intervals of timer interrupts, script files and output files. To let the scaffold test the system in some sequence or repeated times, write a script file of commands and parameters to control the test, parse the script file, test system based on commands or parameters and direct output, intermixture of input script and output lines into an output file. The commands in the script cause the scaffold to call routines in the B, SW, indip component. More advanced techniques. Making the scaffold automatically control sequences of events. For example, calling the print interrupt many times but in a controlled order to avoid swamping. Making the scaffold automatically queue up requests to send output lines by automatically controlling the button interrupt routine, which will cause successive pressing of a button to let the next output line be received from the hardware, the print interrupt routine. In this way, the hardware independent software is controlled by the scaffold, where the button interrupts serve as a switch. The scaffold may contain multiple instances of the software independent code, and the scaffold serves as a controller of the communication between the instances, where each instance is called by the scaffold when the hardware interrupt occurs. For example, the scanner or the cash register. In this way, the scaffold simulates the hardware, scanner or register and provides communication services to the software independent code instances it calls. GDP Remote Serial Protocol. GDB Remote Serial Protocol allows GDP to connect to any target remotely. GDB implements the RSP client side, while the target side needs to implement the RSP server. For example, GDB server. Communication channel for RSP can be a serial or TCP or IP connection. Packet acknowledgement. Each packet should be acknowledged with a single character. Plus sign to indicate satisfactory reply. Minus sign to indicate failure and request retransmission. Interrupt. GDB can interrupt the server transmitting character 0 into 03 between packets. GDB server can ignore the interrupts. RSP packets. Standard remote debug. RSP packets in the remote target command. RSP packets in the load command. RSP packets in the step command. ROM emulator. Circuit for emulating target system remains independent of a particular targeted system and processor using an emulator or ICE. A circuit for emulating target system remains independent of a particular targeted system and processor. Emulator or ICE provides great flexibility and ease for developing various applications on a single system in place of testing that multiple targeted systems. Emulator emulates MCU inputs from sensors, emulates controlled outputs for the peripheral interfaces or systems, emulates target MCU's input outputs and socket to connect externally MCU. Logic analyzer. Logic analyzers are widely used for testing complex digital or logic circuits. They appeared shortly after the first microprocessors were used to find faults. These circuits required the instrument to have access to a large number of lines, more than could be seen using a conventional oscilloscope. Since then, the need for logic analyzers has grown, especially as the complexity of circuits has continued to grow. Although oscilloscopes can perform many of the functions of a logic analyzer, the analyzer is more suited to operating in a digital environment because it is able to display relative timing of a large number of signals. Essentially, a logic analyzer enables traces of logic signals to be seen in such a way that the operation of several lines in a digital circuit can be monitored and investigated. Logic analyzer development. The first logic analyzers were developed out of the need to be able to debug and undertake fault finding on microprocessor-based systems. In the early 1980s, when these chips first started to become widely used, the urgent need arose to develop techniques that would enable the many lines and test points to be monitored simultaneously. Existing oscilloscopes were not able to provide the required levels of functionality. After the early introduction of the first analyzers, their complexity increased in line with the complexity of the circuits being tested. The number of channels grew, their speeds rose, and the functionality in areas such as triggering improved greatly. Logic analyzer key characteristics. There are several key characteristics of a logic analyzer that separate it from multi-channel oscilloscopes and other test instruments. Provide a time display of logic states. Multiple channels. Displays logic states. Does not display analog information. Oscilloscope versus logic analyzer. Oscilloscopes and logic analyzers are very different test instruments. While both have a very similar form of display, that is, displaying waveforms, they use fundamentally different operational concepts. Logic analyzer types. Although development of these test instruments is ongoing and new variants are constantly being launched and many technology innovations are being achieved, there are some main categories into which most logic analyzers can be split. Modular logic analyzers, portable logic analyzers, PC-based logic analyzers. How to use a logic analyzer? Although the operation of a logic analyzer may appear to be fairly complicated at first sight, a methodical approach to the use of one enables it to be set up correctly and to be used effectively. Once the probes are connected, the logic analyzer is programmed with the names of each signal. The analyzer can also associate several signals into groups so that they can be manipulated more easily. With the basic setup of the logic analyzer complete, the capture mode for the data needs to be chosen. This can be set to one of two modes: timing mode, state mode. Logic analyzer trigger. One of the key features of a logic analyzer is its triggering capability. When investigating and debugging complex software-driven digital circuits, it is necessary to be able to see the response of the system after a particular occurrence. Key logic analyzer specifications or specs explained. There are many specifications used to define the performance of a logic analyzer. Fortunately, it is possible to focus on some of the more important or key specifications when investigating the purchase of a logic analyzer to narrow down the choice of the best analyzer for the purpose. This can make the task of choosing a logic analyzer to purchase far simpler. Key points. The major parameters for a logic analyzer that are of importance can usually be defined. Some are included below. Speed, channels, memory. These three areas are normally the key logic analyzer specifications for most applications. Once the requirements in these areas have been determined, then it is possible to reduce the field of possible analyzers. These can then be compared, and any other requirements and specifications can be compared and contrasted. Logic analyzer speed. One of the major requirements for any logic analyzer is the speed of the instrument. It is obviously necessary for the instrument to be able to cater to the higher speeds in the circuits being analyzed. This will not just be the clock speed, and it is necessary to look at the fastest events that can happen anywhere on the circuit under test. With today's high-speed circuits, it will be necessary to the logic analyzer to typically deliver sub-nanosecond resolution. The speed of the logic analyzer is chiefly governed by the timing resolution. This is the smallest time event that the analyzer can see. If the resolution is too coarse, then it will not be possible to see many of the fast occurrences happening in the circuits. The speed of the analyzer must be such that it is able to capture and display a variety of scenarios ranging from transient glitches, any variety of software instructions which may lead to problems occurring, timing violations, or setup conditions. It is often within these areas that the difficult problems can be found, and it is here that the capability of the logic analyzer is needed. Without sufficient speed, many of these elements will not be seen. Logic analyzer channels. Today's digital circuits are becoming more complicated, and they are normally software driven. This means that it is important to ensure that sufficient channels are available within the logical analyzer. Often, high-end processor designs require between 50 and 150 channels to cover all the lines that are relevant to the testing. If a logic analyzer with insufficient number of inputs is purchased, then this will considerably hamper testing. Unfortunately, increasing the number of channels in a logic analyzer considerably increases the complexity of the instrument. Not only is the capture circuitry required, but the mechanical considerations including the probe adapters become more complex. Furthermore, a greater number of channels require increased memory and processing within the instrument. Thus, increasing the number of channels considerably increases the cost and complexity. To help reduce this problem, most logic analyzers have only a proportion of their channels that support the full specification in terms of speed and resolution. As it is unnecessary for all the channels to be able to operate at the maximum spec, reducing the performance of some simplifies the circuitry and reduces the requirements for memory and processing. Logic analyzer memory. In order that the logic analyzer can display the information it retrieves, it must store it in memory. If only a small amount of memory is available, then it will only be able to store short sequences, and this may be insufficient to analyze all the events occurring. Additionally, the greater the number of inputs, the longer the sequences that are needed to be stored, and the greater levels of resolution increase the requirement for memory. As memory can be expensive, it is necessary to gain a sensible balance between memory requirements and cost for the logic analyzer. When looking at the memory requirements for different analyzers, it is necessary to ensure that the additional resolution, sequences, and inputs are not included at the cost of removing some of the essential features that are required. Often, memory requirements may be reduced by turning off some functions such as timestamping, etc., that may be essential for some debugging. It is worth checking that functions that may be essential for some jobs are not removed under some circumstances to save memory, as this can become a false economy. Logic analyzer probes. With a large number of signals required to be monitored, often from a small area on a board and possibly even from one integrated circuit, the design of the probes can be a critical issue. Memory cache. The cache is a special high-speed, low-volume memory that is in close proximity to the processing hardware that it is reserved for. When data is found in the cache, it is called a cache hit. When data is not found in the cache, it is called a cache miss, and the data needs to be accessed in slower memory. The efficiency of a cache algorithm is judged by its hit or miss rate. Embedded architectures include both data caches and instruction caches. Different cache levels exist. L1 or primary cache, L2 or secondary cache, L3 cache. Processor core. The clear trend in hardware design is towards multi-core processors. A multi-core processor includes two or more distinct processor cores to improve performance, reduce power consumption, and achieve more efficient simultaneous processing for multiple tasks. Placing several cores on a single chip allows much faster interaction between them. Direct Memory Access, or DMA. Direct memory access is essential for embedded systems since it allows large quantities of information to be transferred to or from memory without using a core processor. CPU sets up a device such as a disk drive for DMA transfer and disables DMA interrupts. Data is transferred into DMA memory while the CPU is free to handle other tasks. Once the data transfer is complete, the CPU is interrupted to allow it to handle cleanup after the DMA transfer. Floating Point Unit. A floating point unit, FPU, is a part of a processor that is dedicated to operations on floating point numbers. The use of specialized hardware allows faster operation, lower power consumption, and heat dissipation. Typical operations are addition, subtraction, multiplication, division, and square root. DSP. A DSP, digital signal processor, is capable of providing very high performance, low production costs, low energy consumption, real-time operation, high interrupt rates, intensive numeric computations. For specific types of repetitive tasks such as fast Fourier transforms, digital filters, pattern recognition, image processing, and speech recognition. They are key components for many types of applications such as audio, video, and multimedia peripherals, disk drives, and image processing systems for medical and scientific applications. Frame Programmable Gate Array, FPGA. Field Programmable Gate Arrays are two-dimensional arrays of logic blocks connections. A hierarchy of programmable interconnects allows logic blocks to be interconnected as needed by the system designer, somewhat like a one-chip programmable breadboard. Logic blocks and interconnects can be programmed by the customer or designer after the FPGA is manufactured to implement any logical function, hence the name Field Programmable. Configuration. FPGA provides its user a way to configure the intersection between logic blocks and the function of each logic block. Logic blocks of an FPGA can be implemented by any of the following: transistor pairs, combinational gates such as basic NAND gates or XOR gates, N input lookup tables, multiplexers, wide fan-in and OR structure. ASIC, an application-specific integrated circuit, ASIC, is an integrated circuit that has been customized for a specific use. For example, a chip designed solely to run in a GPS is an ASIC. Following Moore's law, a maximum ASIC size has grown from 5,000 gates to over 100 million. Modern ASICs often include entire 32-bit processors, ROM, RAM, EEPROM, flash, and other large building blocks. In certain circumstances, Such an ASIC may be called an SoC, system on a chip. ASIC are designed using a hardware description language, HDL, example Verilog or VHDL, to describe ASIC functionalities. ASIC designs allow the designer to squeeze in more circuitry onto a single chip than if the circuits had been assembled using proprietary chips, which would require more components and board area. This allows lower manufacturing costs, performance, and even some chip designs that would not be technically possible using discrete components. Optimization for embedded system design. In the last years, the diffusion of embedded systems has been growing at a surprising rate. Automotive control engines, cellular phones, multimedia electronic devices are common examples of the pervasivity of such devices. Being widely employed in portable devices, these systems need energy-efficient platforms with real-time performance. Multiprocessor systems on chips, MPSoCs, are among the most appealing solutions to these issues. MPSoCs are multi-core general-purpose architectures developed on a single chip. Each core has low energy consumption and limited computational power. Real-time level performance is thus achieved by extensive parallelization. Given a target application, usually described as a data flow graph, a complete system design aims to allocate hardware resources to processes and to compute a deadlock-free schedule. The problem of allocating and scheduling precedence-constrained tasks on the resources of a distributed real-time system is NP-hard. For this reason, heuristic approaches are widely used, such as genetic algorithms, simulated annealing, and taboo research. However, they do not provide any guarantees on the optimality of the final solution. On the other hand, complete approaches which compute the optimal solution at the cost of an increasing computational effort can be attractive for statically scheduled systems where the solution is computed once and applied throughout the entire lifetime of the system. Since embedded devices always run the same application in a well-characterized context, it is possible to spend a large amount of time for finding an optimal allocation and scheduling offline and then deploy it. Statistical profiling and analysis. Performance is critical in most real-time systems. As any programmer knows, finding the causes of poor performance can be a difficult and time-consuming task. Often, the problem is easy to fix if and when the root cause is discovered. Statistical profiling is an important tool for improving the performance of any program. It is important in general programming as it measures the execution pattern of your application on a procedure-by-procedure basis by taking samples of the execution state. These samples are used to calculate where the CPU is spending its time. This information is exactly what you need to tune your time-critical system for maximum performance. In many real-time operating systems such as VxWorks, each task has an associated stack. The stack is used as a temporary storage area for both local program variables and program execution state. Each time a new function is entered, the processor allocates a new section of the stack to hold the information that function needs. This section is called the function's stack frame. It contains the function's temporary variables and several key pieces of information, including saved processor registers and the return address of the parent routine. A register in the processor called the frame pointer, FP, always points to the currently executing function stack frame. When a subroutine is called, the old frame pointer is saved on the stack. A new stack frame is created and the frame pointer is updated. Thus, at any instant in time, the entire function call history is present on the stack and can be determined by walking down the chain of frame pointers stored on the stack. The sampling clock must be relatively independent of the executing program so that it can generate random samples that can be compiled into statistics to show the program's execution patterns. This compilation is performed by a low priority task on the target. The steady state CPU usage for a typical application profile is only about 3 to 5%, which is by default excluded from the profile display. On-target analysis has the huge benefit of avoiding all network traffic by the tool itself. Thus, networking applications can be accurately profiled. As an example, consider this portion of a network server's execution tree as analyzed by Real-Time Innovations product. Profile scope. There are several tools that allow real-time programmers to collect performance measurements. In addition to function-level statistical profiling, you can use operating system monitors and coverage analysis. All these tools are useful for tuning your application code for maximum performance. While they are very different, their output is quite complementary. Other types of performance tools. There are many tools that allow real-time programmers to collect different performance measurements such as operating system monitors. These types of tools give information quite different from statistical profiling. For example, if your application is thrashing, spending most of its time context switching, a profiler will simply report that most of the CPU is being spent in the kernel. And OS monitor will show you which tasks are switching and display the events. For example, interrupts that are causing the switches. The monitor is clearly more useful in this situation. When to use a statistical profiler? The most important applications for a profiler in a real-time system are identifying excessive usage of the CPU so you can optimize the code or recode to not utilize CPU intensive functions. Timing the execution of a set of routines, for example, to determine what routines contribute to the time of response to some event. Analyzing execution trees. On the other hand, if you have one task hogging the CPU, an OS monitor will only tell you that one task is running most of the time. Statistical profiling, however, will provide a detailed function by function analysis, breaking down the individual routines within the tasks that are burning the CPU. It will give you a direct map of what that task is doing, which routines are being called, what routines they call, and point out exactly where the inefficiencies are. Statistical profiling won't reliably determine if every line of code has been executed at least once. That requires a coverage analysis tool like Tornado's code test or coverage. A profiler measures how much CPU each function in the program is using over a reasonable time period. This is the information needed to speed up the overall execution of the system. Analysis. The accuracy of a statistical profiler's measurement is determined by the number of samples the profiler collects. We seek to understand how long we must let the profiler collect data to ensure accuracy that will accomplish our purpose. We use a well-known result for a confidence coefficient G of a confidence interval E. You need at least n samples of a binary process where n is conservatively estimated by n is equal to PQZ square double brackets 1 plus G bar 2 close brackets divided by E square, where P is the probability of the binary event, Q is equal to 1 minus P, and Z is the inverse of the normal distribution integral function. The binary event is the event that a sample contains the routine in question. What this means is that to be G sure that you are within an error of E, you need to collect n samples. Conclusion. In this chapter, the user has covered the following aspects of interrupt service routines: watchdog timer, flash memory basic toolset, hosts and debugging, remote debugging, ROM emulator, logic analyzer, caches, computer optimization, statistical profiling.